So this is the problem for chapter 5. So I just take a few questions to show how we use uh, Fachner scan and tweets to predict the stability, to predict the transition region for a flow. Okay, for example, for problem 5.7, so for stagnation boundary flow, we assume that U is equal to Kx, estimate the position of Reynolds number where instability first occur. So here we will use U equal Kx because when we have a transition and then we go for turbulent, so the velocity is actually in terms of Kx, means only just a few just only one terms of x. Yeah, if you remember, I think you are now solving the assignment. Assignment is the laminar boundary layers. That's why you will have u over capital U is equal y over delta, and then you will have another or you will have 2y over delta plus y delta square like this. So in laminar boundary layer, you may have two terms like this one. One term plus one term plus another term. But in turbulent, you will have only one terms like this one. So we will learn in chapter 6. So we'll have a single term with a certain value of power. We call it as a power law and so on. So so means that it can be simplified that for transition and also for the turbulent, so we will take U equal Kx is our common assumption for our velocity. So K is the constant. Okay, it can be anything. So and then for example, for this one, for stagnation boundary layer flow, so we assume that U is equal Kx. So estimate the position Reynolds number where the instability first occur. So here it gives you the idea of stagnation boundary layers. So in stagnation boundary layers, you must know that previously when we discussed about Fachner scan, so we found that if the velocity is flat plate like this one, it's laid on horizontal like this. So we assume that the beta is equal to 0. And then if it have wedge like this one, so beta will show you a certain numbers. So and if the flat plate here is in horizontal a vertical position like this one, so we assume is beta is equal to 1. And this is this situation, okay, this position is also called stagnation boundary layer. Why? Because the flow will hit the plate, and then it will create for a split second. So it will have a stagnation velocity. So stagnation velocity means the molecule of flow will stop a while, not so long, just a very, very split second. So it stopped here before it changed its direction to another path. Okay, so we call this one as a stagnation boundary layer because it's start with a stagnation here and then it start to create the boundary layers on the plate. So from here, we know that the beta is equal to 1. So we take this one, and then the theta star, the momentum thickness, is given in this table. So and then another table. So this is table 4.2. Okay, so and then from another table here, okay, we could get the stability because we need to answer this question. We need to ask about the stability. So we take the stability parameter listed by Fachner scan profile. So at beta, because it is a stagnation flow here, a stagnation boundary layer, so we take beta is 1.0, and then we calculate the Reynolds number theta here, critical, as 5,636. So what we can do here is, okay, So from the table, so we take a stagnation here, beta is equal 1.0. So stagnation flow, and then the Reynolds number is 5,636. So, and then we start our calculation by the Fagner-Scan solution. So let's say we have this one. So I think you know that this is the equation for calculate the momentum thickness by the idea of Fagner-Scan solution. So we have theta star equal theta m plus 1 over 2 u over nu x. Nu here is the kinematic viscosity. It is okay, no need to substitute the value yet. So you just remain the u, the nu, and the x as it is. So, and then from the table, we know it is equal to 0.29235. So it means that we look here. So we found that it is equal to 0.29235. So we equal to this one. And then we know if beta is 1, so we could take m is equal to 1. So how to calculate this one? We refer to this equation. So if you substitute the value of beta here is equal to 1, so you will find that m also equal to 1. So, and then we could substitute in this term. So, and then we could have this term. So, and then we could actually the purpose we calculate this one is actually we want to equalize with this. We want to calculate the Reynolds here. So, and then from here we get the Reynolds theta here. Reynolds critical theta here is given in the question as 5,639, and then the equation for Reynolds theta is given by this one. So, and then we know that Reynolds theta is equal to u times theta and times nu. So, and then from here, if we rearrange the equation into theta over x, so we could substitute this term into this term. So if you substitute this term into this term, you could write as this one. So you could write as this one 0.29235 over Reynolds. So, and then so we get it is equal 5,636, and finally we could get the idea of this one. So I mean the Reynolds stability here. Okay, it's right as Reynolds critical. So I change it here. So to make sure that you understand, we are focusing on the stability. So if we calculate, it is around 3.717 times 10 by the power of 8. So means that the instability start to occur, mean the pattern of turbulence start to occur when our Reynolds number is equal to 3.717 times 10 by the power of 8. So it might be a quite large one, so but it is okay because our plate is actually in a vertical condition. So I hope this might be quite confusing. So I hope you try to substitute the value of this one into this one, because if you substitute this one, okay, so we have an extra value of u. Okay, so please try to do it at home for this one. So again, for question 5.8, we are using the same. We are analyzing the same things. We are analyzing about the stability of the flow. So let's say for this one, we are using beta. Okay, for the separating Fagner-Scan wedge flow boundary layer, beta equal minus 0.19884. Estimate the point x over L where boundary layer instability first occur. Assume a low subsonic Mach number. So here it gives you beta is equal negative 0.19884. It is actually about the something like this one. So the flow is coming like this one, and then the flow will flow into this inclined area. So we are we assume that the boundary layer is occur here and then it start to occur again at this surface. Okay, so again, we are start our calculation based on table 5.1. So if we see here, so if we see that the Reynolds number is negative 0.1988, so we found that Reynolds theta is equal to 17. So okay, okay, so means the Reynolds theta is equal to 17, and the Fagner-Scan value, momentum thickness theta is equal 0.58544. So we know that here from here, and also the value of beta equal negative 0.919884 can be taken from this table. So and then we do the same calculation. So this is the Fagner-Scan equation. So we equalize it with 0.58544, and then we assume that m is equal negative 0.09043. So I think you could you could check this by beta is equal to 2m over m plus 1. Okay, if you substitute the value of beta, you will get the value of m, and then we put it here, and then we could get the value of this one, 0.58554. We have x over theta over x, and then we have everything of this one. So and then we could substitute is like this one, and then we could substitute again with the equation of Reynolds theta, and then we could get it is equal to 0.8681 square root Reynolds number, and then we could get it is equal to 17. Then we could calculate the instability. It is equal 384 Reynolds number. So the Reynolds number here is actually the rho UL over mu. So and then if we know the Reynolds number 384, so means for sure we know the density of the fluid, the dynamic viscosity of the fluid, and we have the velocity data, the value of velocity. Now we could assume the we could determine the value of L. So I think we could get the location where the first instability can be occur. Okay, now we go for the transition. So transition means the changes between the laminar boundary layers and turbulent boundary layers. So between the instability and the transition might be, for me, the most important parameter is actually the transition location, because the calculation for turbulent and calculation of laminar sometimes are totally different. So mean you need to understand where the transition occur. That's one. Another one is it can ease our assumption. So if we will learn this in chapter 6. So if boundary layer is, if the laminar boundary layer is quite dominant, so we cannot neglect the existence of laminar boundary layer. So mean we need to calculate both laminar boundary layer and turbulent boundary layer. But if the laminar boundary layer is quite small, just occur in very short region, so means that maybe we could assume that totally is turbulent boundary layer, then we could ignore the existence of laminar boundary layer, so it can make our calculation easier. So mean the transition is quite important. So for common one, we could assume it is as 5 by the power of 10, 5 times 10 by the power of 5. That is the very common assumption. But again, you are doing master course here, master. So if you do research on boundary layer, so mean you need to be very specific. So because the assumption of 5 times 10 by the power of 5, it is a very, very common value. So it will not reflect the real situation. As I said, the surface roughness is actually influence the changes of transition, the determination of transition very much. So let's say we start back, we are using the stagnation boundary layers. So we assume that the velocity is u equal kx. So, and then you could imagine stagnation boundary layers, beta is equal to 1, and then you will have 1. And then we need to predict where transition first occur using the method of Michel as written in the, our textbook, equation number 5 at 5.38. So let's say it start from a table. So I think I no need to show you this table again. So you could refer to table 4.2. You will find that beta is equal to 1, and then you can calculate m is also equal to 1. So and then we could found that the theta star, the boundary, the momentum thickness according to the Fagner-Skan solution is equal 0.29235, and then we could write the equation like this one. Okay, so and then we could calculate, we have the value of r theta here from this equation. So, and then we could equalize it as 0.29235 square root Renault. So, and then if we see Michel solution, so Michel called this as Renault theta is equal to 2.9 Renault by the power of 0.4. So what we do is actually we equalize the idea from Michel with the idea of Fagner-Skan here. So and then we could calculate the value of Renault number x here. So we assume it is a Renault number of transition here. So it is equal to 9.2 times 10 by the power of 9. So what actually we have a lot of equation now. We have Fagner-Skan, we have Twitch, we have Michel, and so on. So I hope you could read your textbook. You will find that it is actually a few famous names who conduct experimental work or research about boundary layers in early 1918, in early 18th and 19th centuries. 19th centuries or 20th centuries. So they start to plot everything based on the Blasius. They start to compare their work with others and so on and so forth. That's why we are going to use this one. So in common calculation, it is okay for us to use the von Karman and also the Blasius. But the limitation of Blasius is the Blasius only valid for lamina. That what we learned. So and then we will use von Karman. And the idea of Blasius by using the analytical. So analytical means they calculate one by one all the parameter using the Navier-Stokes equation. If have time, I will show you how Navier-Stokes equation be used in a boundary layer. Okay, I will always put this Navier-Stokes equation for boundary layers at last, because at least you know the usage of boundary layer until it end, until you could calculate the lift force, drag force, and all the application. Because if I bring the derivation of Navier-Stokes and so on, okay, maybe you just know the idea how to derive the equation, but you cannot see the overall usage of boundary layer later on. That's why we put the equation at the back, because that equation is the derivation is fixed. You could get the value of the derivation in any journals and so on. Okay, so that's why in this course, so we try to using a few equation to compare their result and try to make our analysis. Because as I said, it depends on your object, the surface roughness maybe, and other parameters for your experimental or your in your actual situation. So for Michel, it's his proposed this kind of equation. So they got this equation by plotting their experiment, and then Michel, almost all of them are using the ideas of curve fitting. So means they conduct the experimental, and then they try to get the equation from the experimental data that they have. And then for Michel, he proposed this equation, and then here, the Reynolds number theta here means they calculate Reynolds number here based on the value of momentum thickness. And Reynolds number x here means he calculate the Reynolds number based on the length of the object, length of the plate, mean the value of x exists. So now we have two value of Reynolds theta here, and this also have the Reynolds x here. So we equalize these two equation. So and then we assume that this equation is actually the transition point. So and then if we solve this one, we could get the Reynolds transition for in x-axis. So it's equal 9.22 times 10 by the power of 9. So and then if we make another calculation, so let's say we try to use the Thwaites method. So the Thwaites method is actually another method for us to calculate to get the value of theta. So why we need to get the theta? Because we want to calculate the value of R Reynolds theta. So equation for Reynolds theta is U is equal to U times theta over nu. So we in previous calculation we get the theta here by using the idea of Fagner-Scan, but now we are trying to get the value of theta here by using the idea of Thwaites. Okay. So and then how to get the Thwaites? So I think we have tutorial about Thwaites in previous lesson. So the equation of Thwaites is this one. We have theta square over nu is equal 0.45 over u by the power of 6. We integrate integration u by the power of 5 dx, and then we assume that we substitute the value of u here by kx. So we have kx by the power of 5. And then if we solve this term, we could get it is equal to 0.07 kx, and then to so we could replace the value of k here. So we know that u is equal kx here. So and then we could substitute the value of kx here by u over x. That's why the value of u over x come here at this term. So now we have the theta here. So we substitute our theta in this term, and then we get this one. Okay. So and then we substitute the value. We equalize the value with the Michel here. So we equalize the value with the Michel equation here, and finally we could get the value of Reynolds number transition is equal to 1.764 by the power of times 10 by the power of 10. So if we see here, so it is about 9.2 by the power of 9, and if we have this, it is about 1.7 by the power of 10 here. So I think both value are acceptable.